This is Project 22070, Scrap and Rework Reduction, sponsored by Celestica. Before moving on, we want to introduce the following abbreviations that will be used throughout this presentation.
My name is Masood Al-Kitbi and I am majoring in industrial engineering.
My name is Daniel Morales. I'm majoring in industrial engineering and I am the project lead for this team.
I am Sultan Al-Qablan and I'm an engineering management minoring in system engineering.
I am Sebastian Pavlovich and I am majoring in engineering management.
My name is Martin Cáceres. I'm majoring in industrial engineer and I'm the procurement lead of this project.
Celestica is a contract manufacturing facility that performs design, manufacturing, test, upgrade, and repair of electronic products used in the aviation sector. Celestica has provided the team with a file that contains rejection data across the 4 manufacturing cells, and the team has used this data file that contained about 4,000 rejections to work with, and we want to explain how we narrow down our scope to analyze rework.
Rework is a common issue in manufacturing facilities which can translate into significant savings throughout the value chain by understanding the root causes of failures and implementing corrective actions. The project will look at financial improvements at a contract manufacturing aerospace company. Our goal is to maximize the return on investment of the company by understanding and reducing rework. Hopefully this work will result in a 30% reduction of the site's rework in 2022.
These system requirements guides us for our project. With these system requirements, we have separated the cells into 4 subsets with performing a 3-level Pareto analysis and using an Ishikawa diagram with the 5 whys to get to corrective actions for the sponsors to consider.
DMAIC is the process architecture the team is following in order to achieve an improved process within Celestica. This process architecture helps the team establish a baseline or current state in order to determine where do we want to go and how do we tackle on the rework and the site.
So here's the analysis approach of our project. So basically, since our project is different as we're not building a prototype and we also have no purchase part and no purchase software, we have no part status. We use Microsoft Excel and Notability. First, I'm going to explain how do we use Microsoft Excel in our process to complete this project. We use it to sort the rework and scrap from the quality notification weeks into separate sheet. We use the sort and filters to analyze materials, and we create a 3-level Pareto charts with each data that we have. And then once we've done all of that, we use Notability, which is an iPad app that we use to create a Ishikawa diagram. This is the software that we use during our project. So this is our 3 analysis approaches that we have chosen. We have chosen the Pareto principle, which is the 80-20 principle where we identify our failure is. The Pareto principle talks about roughly 80% fault consequences come out of 20% of causes. And then we are also using the Ishikawa diagram where we want to find the causes and effect of all the problems that are happening in the site. And finally, we want to get the potential root cause by using the 5 whys.
This diagram illustrates the steps the team took to tackle on this project, by first dividing the rejection data into the 4 separate cells. After this, we performed the 3-level Pareto analysis that gave us the top rework performed within each cell, and we followed up with an Ishikawa diagram and a 5 whys combo to obtain potential root causes of rework. The results obtained from this analysis places the team at the analyze/improve phase of DMAIC. This flowchart highlights where the team's effort fall. As you can see, in the assembly process early on the value stream, the team is able to find actionable items to tackle. The assembly process is a big step because when the contract manufacturer is not able to deliver final assemblies to its customers with quality, money is lost throughout the value chain, and it can also impact goodwill in the overall supply chain world.
So for the cabin pressure 3 level, we started with the first level where the area that we found the failure the most, and we end up with assembly. For the second level, we actually categorized the failure, and we found out that damage was the category that failed the most. In the third level, we actually move into the failure, the causes of the failure, or the main failure, and we find out that hole in the diaphragm actually most of the failure, which more than half of the failure. Then the rest is bar and screw and thread.
After narrowing down our scope with the three-layered Pareto, we obtain a problem statement, in this case the diaphragm. We then use an Ishikawa diagram to understand the causes of failure. Normally, this exercise is performed with an interdisciplinary team of people, but the team has worked closely with our mentor in order to perform this exercise. As you can see at the end of the fishbones, there are causes listed such as man, materials, and machine, and the team has decided to go and tackle method, specifically the mold release. After picking a specific cause from the Ishikawa diagram, we follow up with the 5 whys. By asking 5 times why do we have a mold release problem that can potentially cause a hole in the diaphragm, the team is able to identify a potential root cause for corrective action. In this case, the team has decided to focus and tackle FOD, or foreign object damage. By focusing on FOD, or foreign object damage from the 5 whys, the team has proposed a corrective action in the form of 5S. 5S is a methodology for creating and maintaining an organized, clean, safe, and high-performance workplace. A 5S workplace offers multiple benefits, including increased control of foreign object damage or foreign object debris. This slide shows the poster that shall be presented during design day. The poster includes information such as the introduction and a problem statement, materials and methodology used, results, references, and also conclusions.
With the theme analysis performed with the 3-level Pareto analysis principle and the Ishikawa diagram with the 5 whys, we were able to run and verify all our system requirements. We have used analysis method to verify each system requirements, and the table also includes limits and measure values for each system requirements.
To summarize this project, we have completed our Pareto analysis in the main operations, assembly, and of each component that failed for each cell has been identified. We have created a fishbone/Ishikawa diagram, and the 5 whys have been completed for all the cells with its respective potential root causes have been identified. We have also completed the final steps in the transition into the improve phase in the DMAIC process, and we're ready to prepare for the design day.